So hopefully you can read it. So it's, basically this is the approach that we took. We went from linear regression to logistic regression. Now we're going to neural networks and deep neural networks, right? And think of how much time we spent on that, right? So an entire day, this last part we'll do in about an hour. So because you already know how to do this, right? So you already know TensorFlow, right? You should know a little bit of it. You already know how to do a lot of things in TensorFlow. We're just going to tweak things now. We already even have the loss function for the deep neural networks. So that's not even going to change anymore. The only place where we need to focus now is in the inference function, because now we have to add this element of the layers of the model. All right, so let's get started. I did some drawings here, so hopefully they'll make sense. If they don't, look at the other slides. Those are a little bit done by computer. All right, so these are the objectives. So just to convert the logistic regression algorithm into neural nets and deep neural nets. So as we saw in the previous discussion, a logistic regression model is similar to linear regression, right? And as you might imagine, a neural network is similar to logistic regression. So in particular, the only difference is that a neural network has more layers. And the more layers it has, the deeper it is. That's basically all it is. So the layers in between the input and output layers are called the hidden layers, and help to represent the nonlinearity once we start adding these ReLU activation functions. And so therefore, to better discover new features. I think yesterday I did the example, the ReLU is a hockey stick, right? And we were able to fit the data a little bit better. All right, so here I kind of drew this out. It's the easiest way that I could think of doing this. But let's take an image process. So this is just kind of to motivate the intuition, right? So we have a problem. We have a phase, and we have phase, not phase. So we have a two-class problem. So maybe you've never thought about this, right? But a phase is really, and we're not going to use color. We're just going to assume it's grayscale.
I like that you gave him tiny eyebrows.
Oh, yeah?
It's pretty fun.
And so that's the image there in 2D, that one. And then you can see that you can basically take an image and you can stretch it, right? So something that's a two-dimensional array, you can make it into a one-dimensional array, right? If you think about that. And that basically means that we made the whole image the feature vector, right? So what are the features of that feature vector? The grayscale, right? The grayscale values, or the pixels. All right, and then those pixels then become now the model, right? So this is the image now. This image that was stretched into a vector and now fitted here, right? That becomes the input. And then if we were just doing logistic regression, there's no hidden layers here. So basically, each one of those pixels, which is now called a neuron, is connected to just these two neurons here in this layer, the output layer, which represents the class, phase, not phase. Do you see that? That's a basic logistic regression algorithm. However, let's think of this a little bit more. So in the past, people did the following. People would take the original image like this, it had hair, beard or something, kind of messy, and they would apply filters, like edge detection or some filter. So this is an edge detection filter, right? But then also there's fancy algorithms that would look for maybe like, the shadows under the eyes and things like that. And so those shadows would mean that image here was converted into just this image here. You see that? It's still this, let's say it's 28 by 28, as we said here. So this one is still 28 by 28. This is 28 by 28, right? And that's what they did manually. And then they would take these two. So now you have the image. It becomes these two. And then they're both 784 in size when you stretch them. And so they would create a vector of size 1,568. And that became now the input to this. And then they did logistic regression. Do you see that? And so this was the approach for many years. But as it turns out, people discovered that they could model these filters within the same neural network as hidden layers. Right? So that's an important intuition there. So here we have, edge detection. We created this vector. So now this 100568 becomes this one over here, right? So that's the input to the network. And then the network, basically, no hidden layers, is just face detection. And so all of that was manual. It took a lot of work, etc. Okay, so we have that whole mechanism. Now, what's important here to understand is that to go from this image to that image, we applied something in between, which is a filter. And it's actually a matrix multiplication between this and that other figure, because it's like you take a mesh or you take a grid multiplied by something, and that grid, the values there get modified in the space, right? They get rotated and stretched. So that's actually equivalent to doing this. X times something, a W, gives you another X, a modified X or X hat over there. And so if you think about it, this multiplication between matrices here is the exact same operation that happens here in our machinery for machine learning, right? We take a W matrix plus the X data plus a bias, and we literally transform the data. So instead of it being a Y, it is actually now just another X, but an X hat. And this is equivalent to X to hidden 1, or hidden 1 to hidden 2, or hidden 2 to hidden 3, until finally you go from hidden N to the output. All right, they're both consistent in that sense. Are there any questions about that? All right. So we did all of this here, and you can see, again, this was the traditional approach. Took the image, filtered it several times, not just two, multiple times. Penned all those vectors there and do the classification. So filter for shadows would be this times the original image produces this image. However, DNN here, deep neural networks, basically, as it turns out, you have an original image X times the vector produces a new one. So we have this mechanism here, and these filters can be discovered by DNN automatically. Because it's literally like saying, I have this input, I have these filters, which connect here and then to the class, but I can leave these blank or initialize randomly or something like that. If I give it enough inputs and enough, but supervised learning, right? So enough inputs and labels, what's going to happen? It might discover by itself that to detect faces, maybe this filter discovers this edge detection, and this filter discovers this one here. Now, for face detection, which one of these two do you think might actually be the better one? I don't know if you can see this one or that one, right? There's two filters here, obviously. For face detection, which one do you think might be better? For an algorithm, not a person. For an algorithm. The lower one, right? For if you were to say the top one, that's because you're a human. And you have a filter that does this, and you just don't know it. Right? But for a computer, this is still not very clear, whereas if you always see this associated with faces, and you don't see this when it's another label, then you're going to learn that pattern, right? You're going to learn that to recognize that. And so what's going to happen, what might happen is that you have the inputs, you have the labels, and the algorithm needs to fill in these values, right? This filter. But these filters are actually the weights, because we can see here that X times W gives you the modified image. And we already know that the W's are the thing that we learn in machine learning, right? We give it an output, we give it an input, we give it the structure, the objective function, which is important, and then you obtain, bless you, and then you obtain the values that go in there. And if you want to build, and so it may not give you this exactly, necessarily, but if you want to build a good classifier, it has to give you something like this, you see? It has to give you a filter that maybe produces something that you would never even, as a person, even recognize, but the algorithm sees that as this. That pattern, which is the pattern that it associates whenever it sees a face. Right, and so that's pretty much the idea with this. So now, this idea that we had here, because it's, basically it's the weight, you can think of it as adding from the original input to whatever the transform input is, some kind of a filter that, that's the F, that transforms, that makes that mapping, if you will, that makes that mapping. And so it learns to create this automatically in one hidden layer. Now, notice here I put dimensions 784 and 784. But as it turns out, it doesn't have to be that the next layer is 784. It may, because, basically if you notice here, you're wasting all this space, you're wasting all this space, you're wasting all that space. So actually you might be able to capture just this in a smaller space. So that translates roughly into saying that this is not 784, but maybe half of that. And so that's another important intuition. This goes back to when the recommendation that sometimes when you have an input, the next layers should always be a little bit smaller than the previous one. You force it to learn the important things with less space, right? So that's kind of a recommendation, I think. I don't know that there's a proof for that. Right? Yeah, go ahead.
So I just want to make sure I'm
Yeah.
with this. So you're going to have a set of data at the end of this as different classes
Yes.
that represent people. So
That's correct.
Is there a relationship between you start with your 784 feature vector,
Mm-hmm.
and then you have whatever your number is for your output,
Your classes.
tables and your classes.
Yes.
Is there like a heuristic or something that says that, let's say your output classes are 10, that you should have somewhere like less than 784 but greater than 10? Or is there any
I see
type
what
of
you're
heuristic?
saying. I don't know that there's something like that. No equation or anything like that. It's more of a guideline recommendation, but basically make them smaller. Every
It's
time.
smaller than the input in each layer.
And I'll give you one example. CNNs, convolutional neural networks. So they have they have the filter, and then they have what is called a max pooling layer. So you apply the filter, you get an output, and then the max pooling layer cuts everything in half. So if it was, let's say the filter was 32 by 32. In the max pool, now it's 16 by 16. So it's always cutting it and cutting it. Yeah, so it's kind of like this, right? It's going in that way. That's usually the shape of a deep neural net. And as I said, I don't know that there's a proof for that, or some equation, but certainly the recommended guidelines. CNNs are very successful all the time, and that is standard in the way that they're built. Yeah. All right, and this is actually what you were saying, right? Kind of, this is the data set. So if you look face, 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 tree. And so the filter produces this shape, this shape. This kind of is not there like the other ones. And then here there's nothing. So this is annotated with face, 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 and not a face. And so keep in mind, the hidden layer transforms into something like this, and it associates this with face, and this one does not have it. All right, so that's the basic approach of it. So we have our image, the weight vectors, as many layers as you want, because maybe it happens that to go from here to this, you first have to build this part, and with another filter you build the other part, right, the bottom one, and then you have a neuron that connects both of those to create this one. Do you see what I'm saying? That's a possibility. So what I mean is, So what I mean is, this, let's say this part of the filter here, this part, would build that part. And then these neurons over here would build the bottom and the side. But now this neuron over here captures this one and these neurons here, and as it turns out, that is equivalent to the combined image. You see that? And that's the power of deep neural net, because if you had just done maybe one layer, you would have captured this, capture that, but you never capture the whole structure, which is the one that only links with the face neuron and never with the non-face neuron. So then you learn basically this structure, because you always start seeing, when I have a data set, I always have these ones fire, which create that one and that one. They connect with this one, and that is associated with the face. So that's what the deep neural network is learning, right? If that makes sense. And so that's the intuition between having one layer and having multiple layers. So it's really now, some people actually can visualize the neural network. So this is great in images, because they actually take this and then they start visualizing all the layers, and because it's like a transformation of the image, right? And so first in the first layer you start seeing the edges. In the next layer you start to see the edges combine into shapes. And then as you start going further, you start noticing things like just eyes, or more specific features of the face. And that's literally, honestly, what the algorithm is starting to learn. So that can be viewed, and so that's why image processing is where deep neural networks really first developed, because people saw these intuitions. So this is all intuition, nothing to do with the code really, but I just wanted to cover this before we move on. Are there any questions before? Because now I'm just going to move on to the code, and just to give you the last pieces of this whole thing. Are there any questions? All right, so I think that explains the intuition, right? And so now we can definitely go back to just kind of the neural net, right? So far you've built networks like this one that cover this one and that one. So you've built networks. You've built networks like that, right? All connected. Inputs and outputs. But now we are going to start using these hidden layers. You can think of them as the filtered layers if that's more intuitive. They're not necessarily just filters, right? But you can think of them that way. Okay, so deep nets, layers in between the input and output layers are called the hidden layers and help to represent nonlinearities and to better discover new features from the input features. That's kind of what I just said, in summary, in words. For example, in an image processing problem, and I've given this example quite a bit. So architecture. So we can continue to add layers, and this is part of defining the architecture of the deep neural net. So this is something that you can play with today, right? So in everything that you do, I think we did examples that had 4 layers just so that you knew how to implement several. But you can take out layers, add more layers, play with the neurons, convince yourself, add more neurons than you have in the input. See what happens, right? So you can play around with all of that. In theory, more layers can potentially give a model more power to learn from the data and be a better classifier. And that's because, as I said, first you learn edges, then you learn shapes, then you learn eyes. So you have to learn it in phases. Notice, however, that this also means that many more parameters need to be estimated, the weights, right? So keep that in mind. So now you have every between 2 layers, it's a new W, right, of weights that you need to learn. And so that means, very expensive in terms of processing, computing power. So therefore, up until recently, this was very expensive to achieve, right? If you remember, the first perceptron was built in the 40s, I think, right after the computer was created, or 50s, Bell Labs, right? And so the theory has been there for all this time, but it wasn't until 2007 that GPUs became available. Then 2012, when the first code came out that used that this was possible. So now this is feasible. Building and AWS, for instance, will allow us, hopefully if that works, allow this class to actually analyze a large data set with a GPU. Okay. So this is a 2-layer neural network, right? You can see there you have your input, your hidden layer 1, hidden layer 2, and the output. So notice here, this is how in the code we will capture this architecture. Right? So this is very important. This is one layer, this is another layer in logistic regression, but now you will start with X. I've omitted the bias here just to keep this easier to read. So you have the X, which is, just don't forget, the input is always the feature vector, your input. Then the weights are all of these little connections here, and that produces the hidden layer here. Right? And then the next hidden layer, hidden 2, needs these weights, and its input is going to be the hidden layer 1 that you created before, so that's H2. And then the final one, the output, these 3 layers over here, are dependent on the previous layer, hidden 2, times the weights, W3. Right? Yes, sir?
Do you always need a connection from every single node in one layer to every single node in the next layer?
This is called a fully connected network. There are also not fully connected networks. For this class, they're going to be fully connected. But keep in mind, just because we make the architecture fully connected, that doesn't mean that the algorithm is going to learn that all the weights are important. Because at the end of the day, these weights are learned, and some of them could be zeros. Right? That's a possibility. In fact, when the optimization begins, they're all zeros, right? So nothing is connected. You see that? As the optimization starts going, then the weights start changing from zeros to other numbers. So some are important, but the structure is there for you to discover a weight between. So what you want is, so maybe what you were saying is, I want to create a situation where you could never discover a weight between this neuron and that neuron. Right? If you intentionally do that, you could. But you're limiting yourself because it might turn out that there is in fact a connection between that neuron and that other neuron. Right? So that's why you the whole architecture will be connected. At least in our code, if that makes sense. All right? So that's it as far as intuition. Now we are ready just to get back into TensorFlow and to get back into the code. So all we need, really, from everything that we've done before is we need to add one more function. We're going to add one more function, and this one more function is just for readability, because it's going to make us creating more hidden layers a lot easier. If we don't use this function layer, it's just going to be more work for you, right? And so we're going to basically create a function called layer that abstracts the creation of the W, the bias, and that W equal mx plus b through the ReLU function. So all of that is going to be the contents of the function layer. So in our code, we need an efficient way of creating layers that is straightforward, right? So that's really the goal of this. This is the approach taken pretty much by everyone when they write tensor. So there's basically like people that write TensorFlow in functions, and then there's people that just write TensorFlow without functions. So there is like just all the code in there. I think that's a style of how people write code, so it's a preference of what they like. I think this, at least for like keeping a structure that you always know where to go, it's always good to have the layer. But it's your choice. You guys will decide at the end of the day how you do it. You don't. My point is you don't have to use the layer function, actually. That's not necessary. For this, we will use a modular approach and simply define a function called layer. So if you look at the network figures, each layer has neurons connected to other layers, right? In fact, the lines that connect the neurons are the weights. So each neuron in, say, hidden 1 is equal, so this is an important point. Each neuron in, say, hidden 1 is equal to the sum of the neurons in the previous layer. So I don't know if you've noticed that already, that it's a linear sum. Remember, if you have a neural network, doesn't matter if you have 20 layers in there. If there's no activation functions, they're all just linear sums. So at the end of the day, you end up with one single linear function. Right? So that hasn't changed. Okay, so I think I have the code. Yeah, there it is. Here's the code. So this answers a lot of questions that have been asked this week. Right? One of the questions was about the initialization. That's there. You can see it now. The activation function is right there. You see that? It's the ReLU function. So let's analyze. This is the function. It should be in code that you've already used. Again, I'm pretty sure someone's going to ask me, how did you figure out that weight standard deviation? What do you think my answer is going to be to that? I don't have an answer, right? I took the parameters that have worked. So what I can tell you is what are the options? Initialize the weight vector with zeros. Initialize it with a constant other than zeros. Initialize it randomly. Or in this case, initialize it even more like with a normal distribution of some kind. So pick some mean with a standard deviation that you think represents something important about your data, and those are the values that you're going to be picking. Does that make sense, guys? Why is that important? Remember, the weights are directly related to the optimization, right? So they determine where you start. And by starting in more places, in theory, you avoid the risk of getting into local minima instead of the optimal minimum and that kind of thing. So let's just look at the code. I mean, I think this is a great function. So define layers. So notice here that this is no longer x. This is called input because this is where you're going to plug in either the initial x if you're starting the network, or you're going to start hidden 1, hidden 2, hidden 3. Right? So it's basically the previous layer. This function applies to every 2 layers. So every 2 layers. So basically it's going to be the previous one, and this is the output of the new one. Now this is nice actually. We have these parameters, the weight shape and the weight shape and the bias shape. So this is the thing that's going to allow you to change the architecture very easily. Because if you notice, I did say at some point that the weight matrix here is with this weight shape is what establishes what the architecture will be, right? It's like a tuple, right? A list of 2 numbers. So the first one indicates the neurons in the previous layer, and the next one, the number of neurons in the next layer. So this is where you capture architecture. The bias is really always, so whereas, for instance, this would be, let's say, so this would be, for iris, this would be 4, 3, then the bias is always going to be 3, right? It's always the number of neurons in that that second layer. So the first layer and the second layer. So actually, so basically these parameters then indicate we have our input, our weight shape, and our bias shape. Okay, here these are going to be like lists. All right, so this is where we would plug in 4, 3, and 3.
What's the bias shape stand for again?
The bias shape is an mx plus b, right? So it is so when you create a neural net like this, right, and you have one layer here and one layer here, and the w's, this is the x. So this is the output that gets added to the y.
So in the iris database, you said the weight shape is the number of neurons input and the number of neurons you're outputting. So
That's right.
3.
That's right. So this is 4 and 3.
In the iris database, you're saying the bias shape is also 3.
Yes, it is. Yes, because it corresponds to the output. So actually, this should be 3. Do you see that? So this is what you predict.
So you're using the same information twice?
You mean this number and this number?
I thought what you said was the weight shape is the input and output neurons, and I thought you just said the bias shape is also the output neuron.
Right, but it just means no. It just means that we need to create. So remember, we need to create a matrix and a vector here to hold that data, to hold the data for the biases and to hold the data for the weights. That's all. That's all I'm saying here. So, but this corresponds to the architecture as well in the network. So okay, so let me redraw this. So you have a network here, right? That is 4 and two layers, 4 and 3. Okay. So this is X. You need to create the W that holds the weights, correct?
Yeah.
You agree with that? Okay. So that is actually a matrix of size 4 and 3, right? Because, this whole column has 4 weights. Then I look at this one, how many weights does that one need? 4 as well. So that's this column here, and so on, right? But then, once you have the, let's say these 3 here, you still need to add the bias plus B down there. Do you see that? Does that make sense? All right. And so that it just means we need a space, a buffer in memory that also holds these values, because the biases are not actually weights, right? They're another set of parameters. But it just, as it turns out, it's consistent, is what I'm saying. So could you have made some way that, could you do this, for instance? I guess maybe this is your question. Could you do this? Could you say, oh yeah, by the way, bias shape is just the shape of weight shape, but the second one?
Right.
That's perfectly fine.
Okay, so it is.
It always is the same.
Okay.
Is that maybe, I think that was your question, actually.
Yes, that's what I was trying to ask.
Yeah,
Can we
yeah.
have that second?
Yeah, so how would you write that code? It would be, so bias is equal to weight shape 1, right? So weight 1
Yes.
when it's 0 and a 1. So it just takes the one part of weight and assigns it to bias.
Right.
Yeah, that's exactly
I
how.
was wondering.
Yep, that's what it is.
Because as a computer scientist, I think, why would you have to?
Yeah, no, you're right.
Have to?
Yeah, I see your question. I see your question, and that's all right. And actually, some people code it that way. To be honest, I like the fact that I put the numbers in there, because if I do that, I start to lose sight of what the architecture is in my network. If you think about it, I'm going to be like, okay, what was weight 1 again? And I start. So I just like the hard code. Remember, the architecture is something that is going to have 5 layers with 1,000 neurons or something. I mean, it's not going to like break the bank for you to hard code that in there. There's only one architecture. Do you see that? So I think it's actually better for readability to hard code them in there. This is, by the way, just one way of writing this as well. So, you guys are computer scientists. I'm sure you'll start to find more efficient ways of writing your code that make more sense to you. Object-oriented programming, right? So you have a bias object there in the class, and so you can just always call that as well. So yeah, please go ahead.
Okay, so when you said it's 4 and 3 and 3 for the weight shape and the bias shape, are
Yes.
you assuming here that that's just like, if you had no hidden layers in it, now you could call this method for your hidden layers as well and just pass in your weight. Okay, I just want to make sure.
So we build this layer, and we're going to use this layer for every hidden layer.
So you're going to call it recursively?
You're not recursively. No, just call it. It's a function that we call. So when you're building the architecture, you're going to say, all right, so we're getting ahead of ourselves again here, but we're going to say hidden 1 is equal to layer x, I think x, right? I can't remember. And then the next one, we're going to say hidden 2 equals layer, but hidden 1. And the next one is going to say hidden 3 equal layer, hidden 2, and so on. That's what we're doing, if you can see that.
But you could just say, like, output equals layer, x, right?
Maybe. I don't know. Is that a coding trick that you know?
You call it on itself, right? I mean, potentially.
Yes, I write them like this for readability. You're thinking of one single line for efficiency or something, I think. Hey, as I said, you'll find better ways of doing this. But here, let's just get to it. We'll see it in a second, and it'll make more. It's Python code, right? So you can change it. Anyway, so to wrap up, or actually not to wrap up, this function is exactly like what we've done before, except we added these lines above. But if you notice, it is still the same thing. We would always create a W and a bias, right? TF variable or get variable. Get variable is the new version of variable. More efficient for our purposes in this class, pretty much the same. Just think of that. We create a shape. Don't worry about this. Remember that this variable is the Python variable, right? But never forget that when you do this, you're also creating a buffer in the computational graph. And TensorFlow has weird things like naming things in the graph differently, for instance, than naming them in the Python environment. So that's what that is. That's optional. It's an optional parameter. All right. Then you have the weight shape, which is kind of what I mentioned. This is the thing you'll change. And then notice we have this initializer equal w init, because we are building a variable, a buffer, or a tensor of this shape in memory, and we are saying initialize it to some value. In the past, that was all zeros, right? The all zeros. But now it has become w init is what? How would you guys interpret that line? And I think that was your question, right? You had this like a couple of days ago. So this is how you initialize it. So how would you interpret tf.random normal initializer with standard deviation, which is equal to weight standard deviation, which is that? So it's yeah, so some kind of normal distribution, right? So you build a normal distribution, and now you pick values only from that normal distribution. And that's the initialization. Why? Because, as I said, it might be better than just all zeros. Right? So, but can you change this to whatever you want? Sure. Right? So that's entirely up to you. And then notice the bias is also initialized, but to zeros. Right? So anyway, so we create the two variables w and b, right, with the initializers. The important thing for our purposes is the shapes. And then that just becomes matmul. Remember matmul, the most powerful function in TensorFlow, right? The one that literally grabs the GPU, right? Performs the matrix multiplication between input, where input could be, depending on where you are, the X layer, the hidden layer, 1, 2, and 3, times the W plus the bias. And then all of this gets plugged into the activation function tfnn dot relu. Right? Now there's many activation functions that haven't explored, tangents and whatever. This is currently considered to be the best one. I mean, why? That's like a proof beyond the scope of this class, but you can always look it up and convince yourself of that. And it has that shape, so I think I actually do have it in the slides. So yeah, so there is a little bit about this. So in the previous code, we continued to use the equation matmul, and this time pass it through the neural network function tfnn relu. So relu stands for rectified linear unit, and you can see the reference there, Hanloser 2000. Okay, so you can read that paper, get more insight into it. It's an optimal neuron for neural networks, and it serves as the activation function. And then also there's what I said about the init variables that we've defined to initialize and improve the optimization performance. Okay. So going deep, so now this example is about creating the deep neural network, right? So this is the last part. Now we have the layer function. We just added it, and now we're going to go in. So think of the deep neural network, right? The for loop is the same. The variables are the same. Declarations, placeholders, libraries. You know how to do that already. Then we said there's 4 core functions, and then the call of the 4 core functions. Calling the 4 core functions, the same. The 4, if we did a quiz, right, you could list the 4 main functions that we talked about. Inference, loss, training, and evaluate. We already know evaluate. We know training is gradient descent. We established in the previous lecture that the loss function is that softmax with logits, right? Cross entropy. So that's already taken care of. And now all we have to worry about is the inference. And for that inference, we're going to use the little function that we just learned about called layer. So we have defined so much of the code already that there really isn't much left to do, right? That's the truth. All that's left is inference. except to define, and that's where you define the architecture. So except to define the architecture and cost, which we already have. So for the cost function in a deep neural network, similarly to least squared errors in linear regression or cross entropy in logistic regression, we can define the equation or more conveniently use the built-in TensorFlow cost functions. Right? And there it is. In this case, we use TFNN softmax cross entropy with logits. This is defined in the code segment below for the loss deep function. So notice that what you can do in your code is that you can have the regular loss when you're doing logistic regression, or you could also have loss deep, and that just tells you, oh, this is my, for whenever I want to do deep neural nets, I'm going to use this. You can also do inference, and you can say inference deep, hidden layer 3, and you know that's an architecture of 3. But in another function, you do hidden layer 5, and then you try both, right? And all you have to do in your code is change, instead of calling inference hidden layer 3, you call inference hidden layer 5. All you have to do is literally change from one function to the other, and you change the entire architecture of the network in this approach. So that's really handy because it's like you take out one box and you put in another box. Right, so remember I've stressed this, so there's equations or built-in functions, use the built-in. So here is the loss deep, pretty much the same thing. Output in YTF, remember YTF is the real, output is the Y hat or the predicted. So you use TFNN softmax, you compare those two, reduce mean, we already learned what reduce mean does, and then that returns the loss function. Inference, all right, so this is really the question here. Finally, the last part of our code is to define the architecture of the deep neural network. The following examples show how we could define the architectures using multiple layers. The important aspect to notice is that we are treating each layer as a function layer. The output of one function becomes the input of the next function. Right, so I think, right, so let's see. So for a two layers, so for a network of 2 layers, we can define the code as shown in the code segment below. The input to the first layer is the hidden scope. In hidden scope 1 is, and I'll talk about that scope thing in a second, is XTF, which is our data matrix that we defined in previous sections. The result of this equation would be passed to the variable hidden 1, and so on. And there it is. So this is now our function. Now notice I threw in, or people that do this throw in one additional component. And that additional component is to actually add a little bit more information. So there's now this TF variable scope output. So if you think about it, whenever you call layer, you create the W and the B, right? If you remember that, layer creates W and B. They're initialized. By doing that within that variable scope and saying with variable scope, all you're doing is you created W, but before it, now you're putting hidden 2. And then when you do, for instance, so let's take the first one. You do it in variable scope hidden 1. So now you create W, but in front of it you say hidden 1. So now the variable can be referenced in the computational graph as hidden 1 slash W, or hidden 1 slash B. And the next one is the same. You create W, but because you say with variable scope hidden 2, now the name of it in the graph appears as hidden 2 W, hidden 2 bias, and so on.
Hidden 2 dot W, or?
Not dot. I don't know why they wanted it to look like folders. So it's that idea that it's a variable scope. So it's like this is a scope. This is like a folder of the variables for that scope. Do you see that? But
And you can call it in your code.
Not in the code here. In the computational graph, it appears like that. In the code, you don't have to call it like that. So it's something that is done in. I mean, you don't have to do it, by the way. You don't have to do it, but it's something that, because see the other thing is when you create a variable in TensorFlow, you create W, and the next one is called W_1, and the next version of it is W_1_1, if you think about it. So it starts like, but that's abstracted to you, and you might say that's crazy or something, but in I think it's Torch or one of the other ones, you literally have to declare every single variable. So whereas here, notice we didn't have to use W1, W2, W3. Do you see that anywhere in there? No, right? You know what I mean? If I create, you might have thought, instead of using this, I would have done W1 equals something, B1 equals something, the next one, W2 equals something, B equals something, right? We didn't do that. But in Torch, you do actually have to do that. Why did the people at TensorFlow decide not to do that? Because here it doesn't matter, but if you have a really large neural network, that's a lot of variables that you have to keep track of. And so they have to resort to creating a dictionary, and the dictionary has all of your parameters in there. Do you see that? And so this is the approach with TensorFlow. Because again, you're building the computational graph. Are there any questions about this? All right, so basically it's like you can reuse the code to create the variables without really worrying about the naming of it, because TensorFlow takes care of the naming for you. And that's why you add the variable scope, to have a little bit more information there. Because internally, TensorFlow might create its own variable names, but you appended that variable scope. So even if you see something like W1 and W2 or whatever, by appending hidden 2 to that W1, it jogs your memory. Oh, W2, this W2 belongs to hidden 2, so I know which layer I'm talking about. Okay? So that's one of the things that's a little bit difficult to grasp with TensorFlow, but it does make sense actually, because if you program in Torch or one of those other ones, you might wish you had something like this mechanism. All right. So anyway, so now this is the architecture, and you can play with it. So this is what you will be doing today. So remember, the theme today is to do deep neural nets. So you have your inference function over here, right? And you have TF hidden 1, you call layer, you give it XTF, you give it the dimensions, right? And that produces hidden 1. Then you do hidden 2 with layer, which is the input of hidden 1, the dimensions, and then the last one, output the variable here, right? And that produces this output here as well. So hidden 2 through layer goes to output. All right, so can you make this better? Sure, right? You can definitely make this better, but this is just an example of how we can build the neural network architecture. So you can see that the equations are there, and I think it's always useful when you write the code to also draw this little neural network, right? So you have the inputs here, the hidden here, the next hidden here, and the output. And then this way you can keep track of the dimensions a little bit better. That's it. So that's the neural network and the code for 2 hidden layers. I think. Yeah, go ahead. Yeah.
So alpha just comes up with another matrix. You're not trying to get to the softmax output.
That's a good point. So what you're saying is in the last layer you should put a softmax instead of a ReLU activation function. Is that what you're saying?
I'm just trying to figure out because your layer is doing the same thing, right?
It's the same layer. So you can, in this case, then change it to softmax.
So if you're trying to figure, that's what you're trying to figure out, right?
Yeah. Okay.
Classification or something.
Mm-hmm.
Wouldn't I need something that would zero in on class? Not just give it to me.
So instead of ReLU, a softmax. The thing is that ReLU, I think, by definition, produces also zeros and ones. See, that's a little trick that because it's a hockey, and you correct me if I'm wrong, but that hockey stick shape, what is that output?
That's the line.
It's a line, so it produces either 0 or it goes to x, I guess.
So it's binary, right? So if you have three classes.
But each neuron has one of these, right? So it's the output of each neuron
Okay.
that goes here, right? So this goes to each neuron. So it's going to be either 0, constrained at 0, or x is the what? X is the... I understand your question.
It's fine. You're just trying to demonstrate the later.
Yeah. So these, but I see your point. And the fact is that you can do that. So if you want to, so this works. So let me answer it this way. This works, right, for the layers. But if you want to maybe create this and just call it softmax layer, do that. And then guess what? Just plug in what we had in logistic regression because you already have the mechanism to do that. Try both functions in the architecture and see what you get. But they will actually work. But that's a good question, actually. It's a good question because, for instance, in convolutional neural networks, you do it that way. You do everything, and then you always have one final softmax layer. And so now that you think about it, it's something that I'm going to take a look at. But I think a solution to that would just be to do softmax underscore layer, and that strictly put in the softmax function there. Yeah. So good question. Actually, good question. I'm going to take a look at that. All right, so this is an example of 2 hidden layers. So here, using the iris data set, the following definition, we have that. Means that one input vector from the iris data set is connected to the first hidden layer of the model. Therefore, the neurons in the input layer are 4 features per plant in the iris data set. In contrast, for the hidden layer, the neurons represent abstract entities that are the sums of the input features times their respective weights. Right? So that's just a definition of this. The final part, output layer, in the function defines a mapping of 4 abstract neurons from the hidden 2 to the 3 neurons in the output layer, which represent the 3 classes, Setosa, Virginica, and Versicolor.
So in this case, A and
Yeah.
B are 4 and 3.
Huh?
In this case, A and B are 4 and 3.
In this case, A and B are 4 and 3, yes. And you might want to change that A and B to be features and columns. The name. So it's more intuitive, yeah. But yes, so B is the number of classes, A is the number of features. Any other questions? Okay. So here, hidden 2 is defined as a mapping from hidden 1, which has 4 neurons, to hidden 2, which also has 4 neurons. The number of neurons can be defined by the architect of the network. That's you. Right? Similarly, a deep neural network of 3 hidden layers can be defined as follows. Notice that the following statement helps to define the 3rd hidden layer, which is like that. So this is another example. This would be for the MNIST data set, right? So MNIST, I don't know if you guys have heard of it. It's a very popular data set. I recommend that if you want to play with a data set at some point, grab MNIST. It's got, I think, 70,000 samples. It's about images of handwritten digits, 0, 1, 2, all the way to 9. So there's 10 classes, and the images are 28 by 28, which translates into a vector of 784 neurons or features or pixels. The output is 10, and that's why this should be... So this should be 784. This B, I guess, should be 10. I don't know why I wrote 4. I think because I did that drawing as 4. But the actual MNIST is definitely 10 classes.
I
Right.
remember
Yes, sir.
realizing one a long time ago where they only got 8s and 9s.
It only detects 8s and 9s out of all the other numbers, you mean?
You know, one where we compared only 8s and 9s.
Okay. It's a balanced data set, so it's got plenty of examples of all of them. And it does really well. I mean, it gets above 90% on everything.
So I've got a question here.
Yeah, go ahead.
I know you said that the idea is to try and reduce the number of neurons per layer, right?
That's the guideline, yes.
It seems like your first step is a huge reduction from 784 to 10.
This is not probably a good example to go by. I think I just did this because I wanted to write very little. I would recommend compressing. I think your question is compressing it to how much, right? So maybe like 200 to 300.
So yeah, I mean, I would think you're going from 784 to like maybe 500 and then to like
Yes.
and then to 100.
Yes. I agree with you.
Okay.
I agree with you.
And then the measure of a good reduction, that's the numbers you kind of have to play with to figure out what's giving you the best performance.
Yes.
Correct?
Yes.
Okay.
This is a trial and error kind of thing. There's no because.
But you can probably automate that, right?
Sure, like repeat, a for loop, right, of change the coordinates of the network and run it and run it and run it. I'm sure, yeah, you could. I mean, you could definitely have a Python script that calls this Python script and just give it the parameters every time. So I think so. Just keep in mind, just running one of these with really large data takes a long time, right? So, we should see that today when we do the GPU one. Although the accuracy is really good, because again, it's one of those very clean data sets, you'll see that it keeps running and running for a while. All right. So this is the architect. So we're done. I mean, we are literally done. There's no more code to give, I think. So in the last example, a 4-layer deep neural network can be defined with the following TensorFlow code. And those are the lines there. So this architecture is 21 neurons. Remember again, the key thing is you shouldn't get confused of, this is the weight matrix, right? So remember it captures 2 layers. The neurons in this layer and the neuron in this layer. So that's what's important. And then this one and this one are the same, right, as you indicated, and that just captures the dimensions of the bias because that is dependent when you have the 2 neurons to this one, the new neuron, the new layer, sorry. And I even stated it here, right? The number of neurons to define the layer is sometimes considered more of an art than a science. So some experimentation will be required. However, some practitioners recommend that the number of neurons in the hidden layer should not exceed the number of neurons in the input layer, right? So the features per sample. And then I described variable scope. A common approach by the TensorFlow community is to use variable scope to better define the scope of the variables in each layer. This idea of like grouping them in folders or something. This provides efficiencies in the internal workings of the TensorFlow code. And you can see I even added that, right? So you can see now in the this is the computational graph. var2 is now in scope h2. And then if you look at var1, it might be just, if you're reading the graph, you may not know the relationship, but by looking at the variable scope, this is related to hidden 1, this is related to hidden 2. So it gives you a little bit more intuition. Remember that I also indicated that if you really want to view your graph, your computational graph, you can do so with something called the tensor board. I didn't provide any examples of tensor board, but you literally have to start tensor board, and as you're doing things in your code, you have to add information to tensor board. And then once you're done, you say tensor board print stats, and one of the things it'll print is the computation. So that's something in the future that you can do for debugging purposes or for figuring out things a little bit better. All right? So this is the example with 4 hidden layers. Just again, just to kind of, give you a little bit more information, but it's pretty much the same approach. You can see that, and that's, again, I do think it's very helpful to always draw your network first. So draw it over there, put in everything where it should be, and then actually, then write it in the code.